Quantum Computers by Ashish Dahal and Eddie Gray.
So what are quantum computers? Let's start with qubits. Qubits are basic units of information used by quantum computers. They're analogous to the bits used in classic computers, but whereas a bit can have a value of either a 1 or a 0 at a point in time, a qubit can be a 1, a 0, or be in a superposition of both values. Additionally, qubits can use quantum entanglement to communicate with each other over very long distances instantaneously. A quantum computer can use qubits to take computing to the next level. Theoretically, it can perform many types of calculation at exponentially faster speeds and use algorithms that make use of superposition and other quantum phenomena to solve problems classical computers simply cannot even attempt.
The power of disruption comes from quantum computers' ability to implement algorithms that solve extremely hard mathematical problems in record time. For example, integer factoring is a notoriously hard problem for classic computers to solve, but there are algorithms that use quantum computing and can solve the same problems exponentially quicker. The entire web encryption standards would be in upheaval. Similarly, unlike classic computers, quantum computers would be great at modeling protein molecules and even atomic particles, and has great potential to disrupt the pharmaceutical and medical industries. Finally, quantum computing could improve machine learning and AI by leaps and bounds, and promises to disrupt all industries that rely on those technologies.
Quantum computing first began in the 1980s when physicist Paul Benioff proposed a quantum mechanical model of the Turing machine. In 1994, Peter Shor developed a quantum algorithm that could decrypt RSA encrypted communications. Quantum computers have been a dream of decades, with big companies only recently starting to increase their funding into the research. With years or even a decade's worth of research left to go and several steep engineering hurdles to overcome, the two models that describe innovation as a cycle would place quantum computers at the very beginning of their journey, despite the 40 years of prior research. The S-curve model would be particularly lengthy for this technology. The Abernathy-Utterback model would classify quantum computers as being in or maybe even earlier than the fluid stage. The timeline for simulation testing is anticipated to be within the next 3 to 5 years, and actual implementation is anticipated within the next 10 years. Designers are attempting to create a quantum computer which contains 1,000 qubits by 2023, which would allow for extensive simulation. And the goal to reach computational functionality is to reach 1 million qubits within the next decade.
According to the incremental versus radical innovation model, quantum computers would be categorized as a radical innovation because the skills and knowledge required to operate them and create software on them would be competence destroying. Quantum computers would also be regarded as one of the greatest technological advances of the century. The Henderson-Clark model would also classify quantum computers as a radical innovation. Physically, a quantum computer is completely different to a classical computer. The components are different and the linkage between them is different. Software development-wise, quantum computing has to start from the scratch by building the layers of abstractions from physical to machine, assembly code, and so on. It is also completely radical. The TEAS model uses 2 dimensions to calculate who can profit off of an innovation. Due to the extremely difficult technical hurdles that quantum computers face, it would rank low for immutability. Similarly, complementary assets would be incredibly important given that creating quantum computers would require highly specialized labor and knowledge and a great deal of funding. Given the 2 factors, we can conclude that whoever is successful in getting over these hurdles first would be the definitive leader in the quantum computer manufacturing industry.
So what should businesses plan for? Well, at this time, CIOs should be aware of this technology and they should keep track of its implication on their business. They should consider creating a roadmap for it, especially during long-term planning sessions and forecasting for budget and future investment that will be applicable to optimization of operations and supply chains. As for the general public, there are plenty of courses being made available to the public that teach programming on top of quantum computers. IBM in particular has made a prototype quantum computer available for experimentation.
Quantum computers are still in the works and will be for the foreseeable future. However, the potential it offers to shape future industries and the technological landscape has started to inspire a growing number of companies to increase their investment into research in this area.
Thank you.
Thank you.